shapes of molecules. And Lewis dot structures don't directly tell us the shapes of molecules. But if we look at the Lewis dot structures and apply an additional theory, we'll be able to figure out the shapes of molecules. Do the shapes of molecules matter at all? No, we're not three-dimensional beings, are we? We talked, that DNA is a double helix. That's talking about shapes, and partly the way it stores information is due to the way it's shaped. A lot of molecules work that way. The way they function is based on their shape. That's why we care about the shapes of molecules. The theory we're going to use to figure out shapes is valence shell electron pair repulsion, VSEPR. So, valence shell electrons. So we're not going to worry about the core electrons, in other words, just the electrons that make bonds and lone pairs. So that's what the VSE, valence shell electrons. We're going to keep the electrons grouped as pairs, and the idea is two pairs of electrons will want to be as far apart from each other as possible. If I had two clouds of electrons, would they want to be in the same part of space? Aren't electrons negatively charged when they want to get away from each other? That's all there is to this idea of valence shell electron pair repulsions. Electrons are negatively charged. They're going to arrange themselves in three-dimensional space to be as far apart as possible. We're going to start out with really simple shapes. What's the simplest molecule you can think of? I think I heard water, but that's not anywhere near the simplest one. Did somebody just mumble H2, I think?
Yeah, H2 would be simplest.
Wouldn't the simplest molecule be made of the simplest atoms? Hydrogen's about the simplest atoms. 2 atoms is the smallest real molecule you can make. So H2 would be an example of what I'm going to call a linear molecule. If I only have 2 atoms, in terms of geometry, couldn't that be represented as 2 different points in space? 2 different points, doesn't that define a line?
Mm-hmm.
So if I just have a diatomic molecule, hydrogen to hydrogen, HCl, carbon monoxide, anything like that, if it's only 2 atoms, it's going to be a linear molecule. In the lab coming up, they're going to use letter designations to describe the shapes or help you figure out the shapes. If I have something like HCl, I'm going to arbitrarily pick one atom as the center atom. That's our A atom. That's the atom that's in the center. It'll make more sense if I talk about water, H2O, in which case oxygen is my center atom, my A. Then all the other atoms attached to that one atom are going to be B. Water, H2O, that would be AB2, because I've got oxygen in the middle and a couple hydrogens attached to it. Actually, it'll be a little bit more complicated than that, so I'm going to change that statement later on. I'm just trying to explain what the A and the B mean right now. So these, if it's just bimolecular, it's going to be an AB shape. I'm just introducing the term right now. If I went up to something like beryllium hydride, does that molecule follow the octet rule? Beryllium's in group 2A. It brought 2 valence electrons to the game. Each hydrogen brought 1. So I've really only got 4 electrons here to deal with, right? So I've only got 4 electrons. Beryllium is in the second period. It'd be nice if it could follow the octet rule. But if it's only got 4 electrons, it's going to be hard for it to follow the octet rule. Since it's so far from the octet, it's a molecule you've probably never heard of. And other than the fact that it's useful for discussing shapes, I'd probably never talk about it. It is a pretty unstable molecule. So if you're looking at it and saying, boy, that's a pretty weird molecule, yes it is, don't worry gonna give this a designation, how many A's do I always have for that AB designation?
1.
Just one, that's my middle atom, the beryllium in this case. This is going to be an A. Does that A, the beryllium, have other atoms attached to it? Those are the B. How many other atoms are attached to the beryllium?
1 more.
AB2. Anytime I have an AB2, well, that electron cloud, they just don't like each other. So why don't we make them sit on different sides of the room? Pretty much directly opposite each other. In terms of an angle, what does directly opposite each other mean?
360.
180. Would that still be linear? So if I truly have an AB2 molecule, it's going to be a linear molecule as well. The way I'm going to arrange this discussion of shapes, so possible I'm going to start with AB, AB2, AB3, AB4. Is that a reasonable approach? Oh, I brought toys. They shave if I left these in here, right? Simple AB, that would just be like that. This, again, sort of trivial, kind of wasting my time not even holding it up. Does that look reasonable for just something like HCl? Beryllium hydride, two hydrogens would want to be directly opposite each other. So an AB2 would look something like that. So linear, 180 degrees across there. If I gave you carbon dioxide, could you take CO2 and come up with a Lewis dot structure for it? Usually the way this would work on a test would be one of those big giant questions in like 6 parts. Here's a formula. Draw the Lewis dot structure for it. Once you draw the Lewis dot structure, if you get it right, then you can tell me the shape. And then there'll be other stuff that we'll learn later in this chapter that you'll need to throw in, so you'll have to do the shape, Lewis dot structure, figure out the shape. Carbon dioxide is like this. Is carbon the center atom? So carbon's my A. How many atoms are directly attached to the carbon? 2. Could this still be an AB2? It is. What I'm throwing out new is the fact that it doesn't matter if it's double bonds, single bonds, or triple bonds. For the shape, we don't worry about the bond order. Just where are the atoms in 3-dimensional space? Isn't this still a cloud of electrons? And it wants to be as far as possible away from that cloud of electrons. So it's still going to be a linear molecule. Now, if I did something like hydrogen cyanide, 1 single bond, 1 double bond, that would still be one of these AB2 linear shapes. I went up to boron trifluoride. In terms of the letters, what would this be? I just realized I need to add some lone pairs, but you can still tell me how many letters. AB3. I still need to put lone pairs. So if it's not clear, before you can figure out the shape, you have to have the right Lewis dot structure. And I'm hiding a lone pair right up at the top there that you might not be able to see. There are 3 lone pairs on each fluorine. So I've got an AB3. Is that linear? Are those 3 fluorines going to try and get as far apart from each other while still remaining attached to the central boron? So with my toys here, can you already figure out what angle they're going to end up at? How many degrees in a full circle?
360.
360. would I probably want to evenly distribute that 360 degrees? That would get them most equally spread out from each other. So take 360 and what would I divide it by? 3, because I'm gonna spread 3 things equally across that 360 degrees. So they're gonna be 120 degrees apart from each other. Do you think these toys are made to be perfect 120-degree angles?
I sure expect them to.
Are they close to 120 here? Hopefully. It's bigger than 90, right? They all should look about the same angle. Does it look like all the atoms are in the same plane? As long as you don't look too close. Again, if this were a perfect shape, they'd all be in the same plane. If I just look at the 3 outermost atoms, does that define a triangle? I'm going to call this trigonal planar. Trigonal because the outer edges divide the triangle. Planar because all 4 atoms are in the same plane. So an AB3 is a trigonal planar shape. So on lecture test, I want you to do the Lewis dot structure and then just give me a name like linear, trigonal planar, some of the other names we'll be dealing with. In lab, we'll worry about things like AB3, AB2, that sort of thing. These AB designations really make it pretty easy to learn the ideas. You know, it's a good idea, but it's not really what they're looking for out of the lecture book. It's fine to write it down on a lecture test, but just make sure you throw down the actual name as well. So let's see. What if I went with something like methane, CH4? Is that possibly the correct Lewis dot structure for CH4? So Lewis dot structure is correct. Is that going to make it, what type of letter designation would it be? AB4, so a new one? So over here, the angles are 120. Over here, those angles are 180. They're just different indications that we can use to indicate that we're measuring an angle. The arc with a little dash on it is one way I usually use to show that I'm measuring an angle there. Warning, trick question. What's that angle?
90 degrees.
How many incorrectly believe that AB4 has an angle of 90 degrees? Did anybody remember to bring their 3-dimensional whiteboard with them today? Right now, we're working with a 2-dimensional whiteboard, right? So when I draw something in 2 dimensions, any Lewis dot structure is 2-dimensional. Does that sound true? Because we're always drawing them on whiteboards and pieces of paper. If I could somehow get them more than 90 degrees apart, would that be better than 90 degrees?
Yeah.
So if I could go into 3 dimensions and come up with a 3-dimensional shape where the angles are more than 90 degrees, that would be the correct shape for an AB4.
Why don't we do that with the AB3?
I want all of these to be as far apart as possible. For AB3, there isn't really a truly 3-dimensional shape that gets them any further apart. If I take one of these off and start bending it this way, start making it 3-dimensional, isn't that just bringing it closer to what's already there? If I wanted to get these further apart, when I have it bent down this way, the only way I could do that is by bending it back up into a planar shape anyway. So the best way to get 3 things as far apart from each other on a center atom is a trigonal planar shape. But when we get to some of these more complicated shapes, including hypervalent stuff. Right now, we're only talking about things that are following an octet. We'll probably get to hypervalent at some point. Things that are hypervalent will have to go into three-dimensional shapes as well. So if I grab these, grab some more clay. Again, if this is a perfect model set, which you're probably using, all of the angles would be exactly the same. Does that angle look like more than 90 across there? It's not quite 120. I don't know if you can tell that's not quite 120. About 109.5 degrees, about, not exactly, about. So is that more than 90 degrees? Yeah. Okay, so this is actually going to be the correct shape for an AB4. That means I need to go back and redraw this in 3 dimensions.
Is that the trigonal tetrahedral or something?
We'll come up with a slightly simpler name for that. Maybe not a lot simpler, but a little. So I've got one atom going straight up. Could I draw it where I've got one going slightly down and to the left? If we look at it from the angle you're at, I've got an atom straight up. This one's to the left. To your, well, to my left. Okay, now to your left. Down and off to your left. So I'm going to draw it sort of from that perspective. And that's 109.5 degrees approximately. Doesn't this hydrogen come forward from the whiteboard? If these 3 atoms define the plane of the whiteboard, you know, 3 non-collinear points are going to define a plane. These 3 could be defining a plane if you remember some geometry. This one has to be coming forward. So coming forward from the whiteboard. In terms of perspective, as things get closer to you, don't they appear to become bigger? The thing that we use in chemistry to illustrate things in 3 dimensions and say it's coming forward is a wedge like that. And that's saying the hydrogen is closer to you than the carbon is. We could use a reverse wedge to say it's going backwards, but that'd be too easy. Some books use a reverse wedge to show things going backwards, but most books use more of that style of dotted line. It's not a dotted line where they're all in a row. It's parallel dashes. So that represents this hydrogen back here that's going back away from you. So that's how we would represent the fact that it's 3-dimensional. I didn't have to worry about that before now, but now we do have to start worrying about that. So again, on a real test, you have a formula, you have to come up with a Lewis dot structure. How about if you go through, figure out where this is going to fit, and all of that, figure out the Lewis dot structure, figure out the shape, which atom is going to go in the middle? Carbon. I'm going to want the maximum number of bonds to carbon, fewer bonds to everything else.